a question that comes up fairly often in electricity and magnetism is, say I have an electric field, maybe something like this, and I put in a material, maybe a dielectric. And you might ask, what's the new field? What does it do to the field? And that is a fairly ambiguous question because you could ask it a lot of ways. What does it do to the field inside the dielectric? Does it change the field outside the dielectric? Are we thinking about the molecular arrangement of charge in the dielectric, or are we treating it as a continuum? And also, how was the original field created? Right? Here I've drawn sort of a uniform field. You'd say, well, if it was a uniform field, you probably made it like this. You probably had two charged planes, right? With, say, plus sigma and minus sigma. And we stick a dielectric in that, what happens? Well, how are those hooked up? Are those constant charge planes, or are they conducting planes on a battery? Because if you think back to our capacitor lecture, that'll make a difference. If you stick a dielectric in, if these are connected to a battery, they have a constant delta V, that delta V has to drop over this distance no matter what you stick in there. Right? The field might change. Whereas if they're just planes of charge, then the field right here will never change. It has to be, or the field here, due to this, will always be the same because we have a constant charge density. So this will always create the same field right outside its surface. So my point is that to answer this, we have to get more detailed of exactly what we're asking. Okay? To solve a question like this gets pretty deep into the vector calculus, a little further than we would go in a first-year freshman or first-year physics course. But what we're going to do is approach it first in one dimension and then add a couple more dimensions and do enough of the vector calculus to really get a feel for it. We'll get pretty far. We're not going to solve exactly the sphere. All right? So that's what we're going to do in this unit. So let's answer the question, what happens to a dielectric in a uniform? We'll make this simpler by making it a uniform E in, also we'll make it simpler by just doing one dimension. All right? So one dimension means everything is going to be planar. So the field itself will be generated by two planes of charge. So one, let's see, we'll make it nice. It'll have a charge density sigma, and I'll draw it kind of with a hash mark like that to imply that it goes on forever. All right, so there is your plus charge. And we know that if facing that, well, that itself would make a uniform field. Well, let's go ahead and have one over here that is the minus charge, minus sigma. And it also is infinitely large. So the only dimension we really care about is that way. And everything's infinite in the other dimensions. Okay, so we have created our uniform field, and we'll call it, for now, we need to specify which field we're talking about, E external. Every book uses its own little symbols or subscripts for everything. I'm going to call this the external field, the one created before we put anything in here, is just sigma over epsilon naught. I'll go ahead and put an I hat. It's going to be that way from the positive to the negative direction. So this is the field before the dielectric. Okay? So we sort of did this a little bit when we did capacitors. So this time we're going to do similar to what we did for capacitors, but we're going to go further. All right? So now let's put in the dielectric here. And also, it goes on forever, so I'll draw those. And it comes down like this. And like that. All right? And now this thing is inside a field, E external, or the original field was E external. So if it experiences a field, we know what will happen inside. We probably talked about this in our capacitor lecture, is the little molecules and atoms that make it up become a little bit warped. All right? So the electrons get kind of pushed, whoops, to the left, or they get pulled to the left, to the nucleus, the positive nucleus goes a little bit to the right, and you generate little dipole moments, P. inside each molecule. And there's a lot of molecules and atoms in there, so a lot of dipole moments. So the dielectric atoms or molecules, however you want to think about it, whatever it's made of, become polarized. All right, that's okay. And it creates a new field. So it creates an electric polarization field. Field, big P. Okay? So each little atom or molecule gets a little p. All these little p's add up, and you call it big P, where big P is the dipole moment per unit volume. It's just the sum of all the charge sum separation, add it all up, the total quantity of it per unit volume, and of course, big P points in the same direction as all the little p's. Okay. The unit, we can think about the unit for a second. A dipole moment is a coulomb meter, and per unit volume is a meter cubed, so it's in coulombs per meter squared. Okay. So we're creating a polarization field throughout the material. So in this case, it's uniform and always pointing to the right because the dipole density is going to be uniform. There's nothing to cause it to change in different positions as we go. So we just have a uniform P in this case. All right. So there's two kinds of charge to think about in these problems. There's free charge and bound charge. So first let's do free charge. Free charge is usually the excess charge that you put on a conductor or you just place in space that causes the effect you're studying. So in this case, what created this whole problem is the fact that we put these two charge planes here to create the original external field. So that's the free charge. It's usually an excess charge, right? So if you think of this as being a metal plate, this is the amount of charge you added to the plate. Or if it's hooked up to a metal plate to a battery, this is the charge that flowed out of the battery. Or sometimes we just say there's a plane of charge in space. That would be free charge. But what happens is when you bring a dielectric into the field created by the free charge, it creates something called bound charge. Okay, so the polarization, remember we created a polarization field inside this dielectric because of the electric field. The polarization results in bound charges on the surface. Okay. It sort of makes sense physically if you think about it. So really, we're not doing a microscopic model. So I drew atoms and molecules before, but forget the atoms and molecules. We're doing a continuum. So if the material is a continuum, we can acknowledge it has a bunch of positive charge in it, and it has a bunch of negative charge in it. But just think of those as continuous blocks of charge that can sit on top of each other. And when they do that, they're neutral, because there's the same amount. And they're perfectly smooth, no matter how far you zoom in, whatever scale. You never see atoms or molecules or electrons or protons. It's just smooth. If we polarize it, what it means in that case is the smooth, continuous positive charge moved a little bit that way. The smooth, continuous negative charge moved a little bit this way, and they get a little bit exposed on the surface. So you get a little bit of a charge density over here, positive, and you get a little bit of negative over here. And it's just as real as the free charge, right? You think of free as excess charge, that's real, right? You think this, well, this was neutral, so there's not really any charge here. Yeah, there's charge there. Remember my Teflon rod, it had 1 billion coulombs of charge, right? There's a lot of charge in something that's neutral, it's just covered up. So when you polarize it, you uncover a little bit of the charge. So mathematically, what that is you get sigma, you get a charge density on the surface, sigma bound, and it's equal to the polarization field dotted with the normal unit vector of the surface, okay? Because remember, what was our unit for the polarization field? It was coulombs per meter squared. It has the unit of a charge density. So here, we're just saying that you guys got to take the dot product between the P and the N. And in our case, we're doing one dimension, so N is just normal to the surface anyway. So in this one-dimensional case, the charge density is simply equal to the magnitude of the polarization field. And the charge density then we could label as, here on this side we have plus sigma, and I'll put B, to remind you that's the bound charge, and minus sigma B. This is simple in this one-dimensional case, but this is generally true. So you can derive this by just taking a polarized dielectric and calculating the field it creates, and do all this complicated vector calc to get this general expression that's true for all geometries. In this case, it just means we get plus sigma B and minus sigma B. They're not necessarily equal to sigma free, right? That's not something I'm trying to say is true. That would be true if this were a metal. This is a dielectric. Some amount of charge density builds up. It depends on how polarizable the material is, okay? So let's think now. What we're really going to do is apply Gauss's law, but we're just going to think about it. We're not going to write down Gauss's law. And let's think, what does that do to the fields? So let's look. The field outside the dielectric remains E, I'll still call it E external because we're outside the dielectric. It remains sigma, which I'll now call sigma free, over epsilon naught. And since I put a vector hat on it, I'll say I hat. Okay? Now, why does it do that? Well, we know these two created that field. It's two charged planes. Each one makes sigma over 2 epsilon naught, so you add them together. We've done that when we talked about capacitors. But now here we have the same thing again. We have two planes of charge, equal and opposite, and we know what they do. They make a field inside, but they make no field outside, right? Because the field of this one and the field of this one is the same right here, but they're opposite direction, they cancel. It's the same reason that these two planes don't make any field out here, right? They just make it in between. So because we have a one-dimensional system and everything is symmetric and everything is equal on both sides, the field outside the dielectric is not perturbed. That's only true for this one-dimensional simple system, okay? In other systems, the field outside the dielectric can be perturbed. That's the field inside. Let's look at the field, I'm sorry, that's the field outside. Let's look at the field inside the dielectric. And the field inside the dielectric, E internal, equals what? So now, inside the internal field, we basically just have to sum all the fields. Right? Electric fields obey superposition, so it's E external, sigma free over epsilon naught, minus sigma bound over epsilon naught. Because you can see the field created by the bound charge goes the other way. So it's going to make the field internal inside smaller, and if I had to put a unit on it, I'd make it go that way. Okay? Okay, so we're making a little progress. So we seem to be making some progress here. The free charge creates an electric field. The electric field perturbs the dielectric material, creates bound charge on its surface, and the fields change from the external field, which in this case remains constant, will not always remain constant, in the gap, to a somewhat reduced field inside the dielectric. Okay? Except, let's think about this. If we put the dielectric in, we get a certain amount of charge density, a certain amount of polarization based on the external field. But then, actually, the field is not in the material. The material experiences is not the external field. It's the internal field. The little atom, if we go back to our atom for a minute, it got perturbed. It doesn't know what's going on. Right? It doesn't know that this is an external field or internal field, or if the field's coming from its neighbors being charged or the surface. It doesn't know about bound charge. Right? All it knows is it has to find a value to reach. Right? So we have a little bit of a problem, but sigma B depends on E internal. And E internal depends on sigma B. So there's sort of this circular problem. We can't just keep going around in circles. So to solve it, you would need to think about the microscopic view of what's happening in great detail. But for the macroscopic picture that we're doing, the macroscopic model, you just define just define the dielectric constant. The dielectric constant K, the unitless number that you can use to characterize a dielectric. And the dielectric constant will tell you it's how much it goes down, it's how much the field changes. E internal is whatever you apply externally, and it's reduced by a value K. That's what the dielectric constant is. Okay? So if you have that, then you can go back to our former equation. So we could say, in that case, then before, what did we have? Before we had sigma free. Oh yeah, we could say that E internal, which we now know is sigma is the free charge density over K epsilon naught. Right, so that's E external is sigma free over epsilon naught. We're just dividing it by the dielectric constant. That's equal to what? That's equal to the external field plus the polarization, the field the polarization creates going back. So the external field, well, that's just sigma free over epsilon naught. And then we subtracted the field due to the bound charge, which was sigma b over epsilon naught. Right. And what you can do is you can flip these around to figure out what surface charge density will build up on the slab in terms of the free charge density. And you get that the sigma b, the charge density that builds up, is K minus 1 over K times sigma free. Okay. So that is a little bit of an answer of what happens. And we don't get into the deep solve this circular problem. That would require a microscopic model. We just have a macroscopic model. We just say it goes down. How much? This much. Why? Don't worry about it. It goes down by that much. We measured it. Okay? That's how you do it macroscopically. So that is it for our simple one-dimensional model. We saw what happened, right? We put it in, polarization, we got some surface charge, the difference between bound charge and free charge. Now we understand that. In this special case, outside it stayed constant, inside it went down, and we even have a way to measure how much it goes down. So that's one answer to the question of what happens when you put a dielectric in an electric field.